Hello and welcome to my video lab report for Experiment 5 on Faraday's Law and magnetic braking. The primary purpose of this lab is to observe and collect real-world data of a powerful bar magnet falling through a conductive aluminum foil tube, model the physics computationally using VPython, and evaluate how the induced currents create a magnetic braking force. As a quick preview of our main results, the magnet falls dramatically slower through the tube than it would free space, quickly reaching a steady terminal velocity of approximately negative 0.22 meters per second and taking 1.211 seconds to fully exit the tube. To understand this system, we rely on several fundamental physics principles. First, the bar magnet is modeled as a point magnetic dipole, creating a non-uniform magnetic field. As the magnet falls, the magnetic flux passes through the cross-sectional area of the tube changes over time. According to Faraday's law, this time-varying flux induces a Curly electric field and a corresponding electromotive force, or EMF, around the tube. This EMF drives a current, I, governed by Ohm's law, and the material's resistance. Finally, by the Biot-Savart law, the magnetic field of our falling magnet exerts an upward magnetic force on these current-carrying rings. By Newton's third law, the rings exert an equal and opposite upward braking force back on the magnet, opposing gravity. For our setup, we explicitly define our system as the moving bar magnet, while the surroundings consist of the aluminum foil tube and earth. We assume the aluminum tube remains perfectly static throughout the drop. Our initial experimental conditions include a tube length of 0.27 meters, an inner radius of 1.5 centimeters, an aluminum foil thickness of 2 centimeters, and a magnet mass of 23 grams. In the real-world experiment, we record the magnet dropping vertically through the tube using a smartphone camera. By scrubbing through the video timeline, we can precisely subtract the entrance timestamp from the exit timestamp to find the average real-world time. Next, we look at how this was modeled computationally using Web VPython. The tube is modeled as a vertical stack of individual non-interacting conductive rings. Within our simulation loop, for each time step, the code dynamically updates the distance between the magnet and each ring to compute the analytic time derivative of the magnetic flux d phi dt. This tells us the current induced in each ring. Crucially, to get the physics right, the magnetic force on the magnet must push upward to oppose its force. In our code, this means ensuring that the magnetic force on the ring calculation uses a positive sign convention, so it correctly acts as a braking mechanism rather than accelerating the magnet downward. When we run the corrected simulation, the output data makes perfect physical sense. Looking at the velocity versus time graph, the magnet initially accelerates downward due to gravity alone. However, as it enters the tube, the induced magnetic braking force quickly grows until it perfectly matches the gravitational force, F net equals 0, bringing the magnet to a flat terminal velocity of approximately negative 0.22 meters per second. It maintains this constant velocity until it exits the bottom of the tube, where the force drops off and the gravity takes over again. The total simulated time in the tube is 1.211 seconds. When comparing this to the real-world trial, any difference can be attributed to human error in video time tracking, air resistance, or structural imperfections in the handmade foil tube, which can be made more accurate by modeling the tube as a continuous system rather than in discrete segments. To conclude, let's address our what-if questions. First, what if the resistivity of our conductor were reduced as close as possible to 0? By Ohm's law, if the resistivity approaches 0, the electrical resistance of the rings drops to 0. This would cause the induced currents to become incredibly large. Consequently, the upward magnetic braking force would balance gravity almost immediately, slowing the terminal velocity to near 0 and causing the magnet to practically hover or take an exceptionally long time to fall through the tube. Secondly, what if holes or slots were cut into the tube? Cutting slots would physically break the continuous circular paths around the tube. This would severely disrupt or entirely prevent the flow of ring currents along those cut areas, lowering the overall induced current, reducing the total upward magnetic braking force, and causing the magnet to fall through the tube much faster. Thank you for watching.